Alrighty, let's do this too now. You have two of them. They want you to differentiate each function with respect to x. So let's do the first one. So for the first one, we have the derivative right here. Derivative of arc sine is this bad boy. So let's go ahead and do this. So what we have right now is, because of 1 over the square root, 1 over the square root, and then we have 1 minus x squared, so 1 minus, and then the x was 4x squared, so all that being squared. And then for the bottom one, it's this, so I did the exact same thing. Wherever I saw an x, I put x cubed, and I'm done, right? Right. No, I'm not done, because we have to multiply. We have to multiply by the chain rule. So, what's the derivative of 4x squared? That would be 8x. What's the derivative of x cubed? That would be 3x squared. Boom. And now you are done. I mean, you can also change these up real quick. So instead of putting 1 minus 4x squared, you put 1 minus and then 16x to the fourth. And this one would be x to the sixth. Alrighty, I believe I'm done now. Just making sure. Yeah. So just make these substitutions, and this one goes right there, and then all this stuff goes underneath all this. And let's move on. Alrighty, so we have a few definitions we have to go over. Differentiability at a point. Function f is differentiable at x equals c if and only if, meaning both ways work, f prime of c exists. So let's talk about that whole if, the if and only if. The statement could have written as, if function f is differentiable at x equals c, then f prime of c exists. But because we have that if, you can also say that if f prime of c exists, then f is differentiable at x equals c. So that's how this whole thing works. You can just pretty much say the statement vice versa. Differentiability of an interval. If f is differentiable on the interval, if and only if, for every x in that interval, the f prime exists, or f is differentiable. Okay, it's pretty straightforward. I know I didn't read it correctly. Let me just read it one more time. The function f is differentiable on the interval if and only if it is differentiable for every x value in that interval. And then f is differentiable if and only if it is differentiable at every point, every value of x in its domain. Okay, so the first and second statement are virtually the same thing, except this one doesn't have a specific domain, where this one does, but they mean the same thing. Alrighty, now we have this statement right here. If f is differentiable at x equals c, then f is continuous. Okay, so notice there's not an if and only if. So the statement I can make right now is that if it's differentiable, then I know for sure that it's continuous. But I cannot go the other way around. I can't say that if something's continuous, it's differentiable. There are a lot of functions that are, for instance, this one. You see that strong hook right there? The limit on either side for the slope would be different. If you did the slope on this side, it'd be negative. If you did it on that side, it'd be positive. So it's not differentiable at that corner. But because the value exists, it is continuous. So this would be an example where if you have something that's continuous, it would not be differentiable. But if it is differentiable according to this property, then it definitely is continuous at C. The contrapositive would be vice versa, but negated. So if the f is not continuous at C, then f is not differentiable at C. Contrapositive is a really cool concept. I really like it. So if I made the statement that if Mr. S eats cheesecake, then Mr. S gains weight, the contrapositive would be if Mr. S did not gain weight, then he did not eat a cheesecake. So I reversed the order, and I made them both negative. So over here, I first talked about, I forgot what I talked about here. I just do another one. If Mr. S runs the red light, then Mr. S also hits a puppy. If Mr. S didn't hit a puppy, then Mr. S didn't run a red light. So I reversed the order and negated both statements. Okay. And then, anyways, these I'm not even gonna talk about them because it's already stated that these are not true. Let's move on. State whether a function is differentiable if it's differentiable or continuous. Alrighty. So over here, sharp corner, it's not differentiable, but it is continuous. Over here, it's not continuous and therefore not differentiable because it has to be continuous in order to be differentiable. Oh, it's a negation, if you remember. We were just talking about that. Okay. Over here, I'm guessing this is an open dot, so it's not continuous, therefore not differentiable, because that's the contrapositive of the statement. If something's differentiable, it's continuous. And, are we talking about right here? Okay, so this one is definitely differentiable because you could find the slope here. It would be like negative, I don't know, negative 1/2. But because it's differentiable, it is also continuous because of our property that we talked earlier. Alrighty, so over here, prove that this function is continuous at x equals 4. That's easy. I mean, if I can prove that it has a derivative at x equals 4, then it's differentiable at x equals 4, which would make it continuous as well. So we have the derivative being 2x minus 7. This becomes 2x and that becomes negative 7. The 13 goes away. You plug in 4 and you end up x minus 7, which is 1. And then, since you found a derivative, it is differentiable at 4, and since it's differentiable, it is also continuous at 4. Alrighty, so is the function differentiable at 2? Justify your answer. Oh, it's not. Now we have to prove that it's differentiable. Well, if I can prove that it's not continuous, then it's also not differentiable because of the contrapositive. So, let's do that. Since the denominator would be 0, but it would cancel out. So you see how this one would cancel. It wouldn't be a vertical asymptote because it cancels, but it becomes a removable discontinuity at x equals 2. And because that means it's not continuous, it also means that it's not differentiable at 2. Alrighty, so let's see what this one's all about. Use one-sided limits to find the values of the constants a and b that make the piecewise function of f differentiable at 2. Check your answer by graphing. Okay. Let me think about that for a second. So I think we're gonna have to take the derivative of both and then find out what makes the derivative a value. Because if the derivative exists for both sides at the same point, then it should also be differentiable. Alright, so let's get that started. Alrighty, so we first looked at the first statement, so it has to be continuous first, because if it's not continuous, it's not differentiable. So in order to make continuous, we make the first function equal to the second function, and that will give us an equation that looks like this. And then we took the derivative of each, and then made the two derivatives equal to each other. So here's the first one, that's the second one. Got a second equation using it. Then you can just use substitution, so just take one equation, solve it for one, and then plug it into the other. So, and we ended up with this, solve for A, and then plug it back in here, and then solve for B, so now you have your A's and B's, and you can simply plug them into here to have your, that's what they want, right? Find the values of constant. Oh, okay, you don't even have to do that. You just leave it at, here's my A, and here's my B. Alrighty, I think that's it. That's the video. See you guys tomorrow.